we've got certain quantities that we've defined so far this year. We've got kinematic quantities, and we spent the first part talking all about kinematics. Kinematics is just describing how motion takes place in time and space. And then we moved on to Newton's laws. And in Newton's laws, we find out, about forces and how to use force to figure out how to solve certain problems. And then in chapter 7 and 8, we moved on to energy, work and energy. But today we're going to define another quantity, momentum, that allows us to solve really interesting problems. And this is, momentum is one of these really important major ideas. And it's also going to relate back to Newton's second law. What was Newton's second law? Let's review a little bit. Right, the net force is equal to mass times acceleration. And this is how we wrote it down. This is not the total truth. I did not tell you the truth. This isn't wrong, but it's not complete. And it's not how Newton described his second law. What we're going to do today is we're going to develop an idea that is going to be the complete idea behind Newton's second law. So let's get to it. Remember Newton's third law. Let's say I've got some kind of object in space. This could be a planet, or it could be an atom, or a galaxy, doesn't matter. Some object that's moving and has mass. Okay, and here's another object, object 2. And let's just suppose these are like stars or something, and they're applying a force to each other. There's an interaction between the two of them. Maybe this one is moving this way. Here's V1, and this one is moving off in this direction. Here's V2. So there's my velocity vectors, and this has a certain mass m1 and a certain mass m2. But let's say there's some kind of interaction going on here. Now, if these are atoms, it could be an electric force, which we're going to study next semester. Or if they're big objects like planets or stars, it could be a gravitational attraction. But in any case, let's say they're attracted to each other. So you've got equal and opposite forces acting on them. This is the force of 2 on 1. This is the force of 1 on 2. Okay, and these two forces, Newton's third law says that for every force on one object, there must be an equal and opposite force on another object. Okay, and they're equal. And so if you say, well, the force of 2 on 1 is equal but in the opposite direction of the force of 1 on 2. Well, I'm just going to do a little bit of mathematical manipulation here. I could say, hey, the force of 2 on 1 plus, add it to both sides, the force of 1 on 2 is equal to 0. Does that make sense? Okay. And so now let's say that this is my system. This is my whole system. It's an isolated system. That is nothing outside of my pretend universe here is having any influence. There are no outside forces acting. There's no matter entering or leaving my system. This is my system, these two objects. So if that's true, if I drew a free body diagram of this guy, this is the only force acting. So it's a net force on object 1. And the force of 1 on 2 is the net force acting on object 2. Does that make sense to everybody? This force, now remember, this arrow represents velocity. This arrow represents force. Here and here. Well, if that's true, then this is the net force acting on object 1. So I'm going to say this is equal to m a1. That is, this is the acceleration of object 1, and this is the mass of object 1. The force of 2 on 1 is the net force, and so it's equal to ma1. Okay, that's kind of what we said before. And, you know, this Newton's second law, it works. It's true. Now, let's, I think by the same reasoning, this is the mass of 2 times the acceleration of object 2. And that's going to be equal to 0. So I'm just following, you just have to follow a little chain of logic here. Well, what is the acceleration in object 1? Didn't we say the acceleration on an object is the rate of change of its velocity? Right? This acceleration represents the rate at which I'm going to change this velocity vector in terms of direction and magnitude. And the rate of change of velocity can be written as dv dt. Okay. Plus m2 that, of course, will equal 0. Now the mass, m1 and m2, the masses are not changing with time. So there's nothing wrong with me putting this mass into, in with the velocity. Nothing that says I can't do that. So here's my derivative operator, and I'm just going to move the mass in there, m1, v1. Plus ddt of m2 v2. Okay. And this all equals 0. Are you with me? I'm just doing what math says I can do. The math gods say this is okay. Well, the sum of the derivatives is the derivative of the sum, right? Or the sum rule in taking derivatives. So I can take this, and just to make room on my paper, I'm going to go up here. So that turns into the derivative, the time derivative of the sum. Okay. This is a big deal. When I take the derivative, the time derivative of something, and it's equal to 0, that means that thing that I'm taking the time derivative is equal to 0. That thing, this thing, is constant with time. It's being conserved. So this quantity of mass times velocity, this quantity is being conserved in my isolated system. This is a big deal. Okay, whenever you see some quantity being conserved, even as other things are changing, that's a real advantage. You know, that's a real insight into how the universe works. So we have a name for this, the mass of an object times its velocity. Mass times velocity. We call it, by definition, is called momentum. So momentum, how's that working out for you? You getting it done? Okay, mass times velocity is called momentum. Now, we don't want to write the words out, so we need variables to express this. Let's put the mass times velocity over here. Obviously, we use m for mass, lowercase m. We use v for velocity. Velocity is a vector quantity. Now we need a variable name for momentum. the stuff that we're defining right now. Momentum. What would be a logical letter to represent momentum? M. Well, that would be confusing, though. M equals M times V? Or we could make it capital M. Well, it's still a little confusing. So somebody had a great idea. Let's use the letter P. Why? It's available. But what about power? Oh, that's capital P. We'll use lowercase p with a vector hat.
It's like fancy P, so it's not even its own thing anymore.
All right, so that's this is the letter we use to represent momentum. Sorry, wasn't my choice. Okay, don't shoot the messenger. Now, what about the units for momentum? Kilograms, meters per second. We just leave them like that. Like, remember we said mass times acceleration defined what a force, my units for force, right? Mass times meters or kilograms, meters per second squared. We called that a Newton. Well, we don't have a unit for momentum, and I don't know why. Momentum is so basic. I think we should call them lakes. I've written letters suggesting that, but they've fallen on deaf ears. Yes, because I think somewhere, everyone should have some kind of unit named after them. All right.
No, but there's no special unit for like a spring constant. It's newtons over. Newtons
per meter. I know. We can maybe we can call them All right, but in any case, this is the equation that we use for momentum. And so if I go back to this, I can say this. I can say, well, the time derivative of P1 plus P2 equals 0 in this case. Now, what does this mean? I mean, what was the basic assumption that was made to get this big idea going? That my system was isolated. That is, I have a two-particle system here, and I've isolated it from the rest of the universe. The rest of the universe is leaving it alone. There's no exchange in mass. There's no exchange in energy. There's no force. It's all by itself. Isolated system. So what this is saying is that if I add up the momentum of the particles in my isolated system, the sum of those momenta is the plural for momentum, is constant. Now, if I let P initial be the total momentum in my system, well, the initial momentum of my system will be equal to the final momentum of my system, equals a constant value. If you have an isolated system, the momentum in that system will not change. Now, the momentum of the individual particles in that system can change. Look, if this is gravity, this object's momentum is going to change. This object's momentum is going to change. But when I add those changes together, they will cancel out to get zero change in momentum. So this gives us the law of conservation of momentum. Momentum is conserved in an isolated system. Now, this adds to our conservation laws. We had a conservation of mechanical energy. We said if there are no non-conservative forces acting on your system, or if there are no non-conservative forces doing work in your system, then mechanical energy is conserved. And here's this one. If you have an isolated system, momentum is conserved. Well, what if you have a system that isn't isolated? What if I have a net force acting on an object? Well, in fact, if I go back to my isolated system here and just say, oh, here's my system now, I'm going to make object 1 my system. Is object 1 an isolated system? No, because this object is applying a force to it. So we can play around with systems in our imagination. We can say, oh, let's isolate this. Well, let's just look at this object. Oh, but this object has a net force on it. Well, I can look at object 1. If here's my object 1, well, let me start on a separate sheet of paper. If I have an object, a particle, okay, and it's got a net force acting on it, okay, then its momentum is going to change. And the rate at which, this object, maybe here's its velocity vector and it has a certain mass. So mass times velocity, if I say, well, let's take, this has a certain momentum. Its momentum is going to change. Let's look at the rate at which that momentum changes. Well, this is mass times velocity, right? That's my definition of momentum, is mass times velocity. Well, let's take the time derivative of this. But look, what is m times v? That is a product, right? Momentum is defined to be the product of mass and velocity. So let's take the derivative of it. I have to use the product rule. It's the first times the derivative of the second plus the derivative of the first.
You're on the screen.
Thank you. Times the second. Okay? Now, this is a very interesting equation. Equals, well, this is m, and what is dv dt? dv dt is acceleration plus, now dm dt, what is that? That's the rate at which mass is changing.
Zero.
Now, in this case, it's 0. In this case, 0. Now, I'm going to declare it to be 0 in a second, but I'm going to use m dot. And this is what they use in industry. You can call it dm dt, just leave it like that, but m dot, it's the mass flow rate times velocity.
The mass
Flow rate.
So
It's the rate at which mass is changing.
So this is like if the mass actually was changing, it'd be that.
Exactly.
Okay.
Now, this is what, here's my force. This is what a net force actually does. This is Newton's second law. Newton's second law really is this. The net force is equal to the rate at which momentum changes. Newton's second law right here. No more modification needed. This is it. But in the vast majority of cases, what's true about m dot? What's true about the mass of my particle?
It's constant.
It's constant with time, right? So m dot becomes 0, and you're left with F equals ma. But can you think of an example of a situation where you get a force because of m dot. Yes?
A plane breaking up before it crashes into the ground.
A plane before, well, no.
That's like
Well,
the wings break off.
perhaps, that's not what I'm thinking, though.
Maybe if
Giant, spinning thing.
Okay, I'm just going to tell you because A, we're running out of time, and B, you guys are nuts.
What if Jello is flying through space?
No Jello in space. Okay, we don't have to, I only got 6 minutes left. I should have known better. Okay, now, have you ever, imagine a garden hose,
Okay, that's different.
okay?
Jello.
Okay. Here's the little nozzle on the end of the garden hose, right? You can. Now, it shoots water out really fast. You turn it on, and actually, I've got a little hose attachment that goes on here, and it's cone shaped, and so it makes a little tiny nozzle there, and it shoots water out super fast. Have you ever held on to that hose, and it pushes back on you? Do you know what I'm talking about?
Yeah.
How many of you have never held on to a garden hose when it's turned on full blast and you feel the force? Okay, your homework is to go home and find a garden hose and play with it.
Okay, wait, how high is your water pressure? Because I don't feel
Really high water pressure. Okay, I'm not going to get into all that, all right? Now, by the way, if you're a firefighter, the pressure and mass flow rate out of those hoses is so high that if you accidentally let go of one of those hoses, it'll start whipping around and it can kill you. It's dangerous. This is the thrust out of the back end of a rocket. Now, what have you got here? You feel a force pushing back on you, right? But there's nothing accelerating here. There's no mass times acceleration here. Where's the force coming from? It's coming from m dot. If you take the mass flow rate coming out of a hose and multiply that mass flow rate times the velocity of the water leaving the hose, you're going to get a force. We call it thrust. Like a jet engine has thrust. A rocket engine has thrust. A hose has thrust. Now, it's not all that intuitive. I mean, you're used to dealing with accelerations caused by forces pushing on things. But this is part of your everyday experience, and you may wonder, where does that force come from? I mean, what's going on here? Well, Newton's second law predicts it. If this is my system right here, I've got a mass flow rate out of that system. I've got a rate of change of mass from my system. Take that mass flow rate, multiply it by the velocity of which it leaves, and you're going to get a force.
Wait, so I don't think how the mass changes.
Mass, here's my system. Mass is leaving the system. Yes?
Oh.
So but the direction of the force, is that backwards? I meant, where is the direction of the force, like, really? Is it towards your, is it towards, like, the hose?
In order to keep this stationary, you got to push it to the right because the force is to the left. Now, that's a good question. I'm not sure how to answer that, I'll be honest.
Wait, okay.
Especially with 4 minutes left.
Isn't water inherently the other side at the same rate that it's going down?
But we're dealing with one system. That's like another system, isn't it?
Yeah, I'll just include that system.
But then you
The whole hose is in my system. Yeah, I suppose you're right. Yeah.
Right when you turn it on, water is rushing into the system.
Yeah. It's if you have a situation where you're throwing mass away, the rate at the velocity times the mass flow rate will get you a force. It really does. It does work, and I'm just going to have to leave it there. Okay. Now I'm going to look at this, and I only got 3 minutes left, and so I may have to. You know what? I'll save it for next time. So this, really what I've covered is 9.1. 9.2 is on impulse and momentum. So you can read that and start working on the homework. I will lecture on it next time. So we'll have to do 2 lectures next time. Well, not next time I lecture, because what are we doing on Tuesday? Yeah. Okay, that's it for today.